Okay, free body diagrams. These diagrams are not in prison, they are free body diagrams. They are free to be. What's a free body diagram? A free body diagram shows all the forces acting on an object or on a system of objects. Okay, let's talk about this thing called center of mass. Center of mass is the point on which gravity acts on an object. And you're like, what? Doesn't gravity act on like the whole object? Well, yeah, it does. But if you were to squish an object to one tiny point, squish it down to one tiny point, and that point would behave just like the object itself,
under the influence of gravity,
that point is the center of mass. So if you squish down an object to a point where its center of mass is, then gravity acts on that point on the center of mass the same way it acts on the whole object. So an object squished down to its center of mass is affected in the same way by gravity. And every object that has mass has a center of mass, or a point on which gravity acts. So when you're talking about forces acting on an object, or when you're drawing free body diagrams, we can draw our objects as a point, like where their center of mass is. So where is the center of mass in an object? So the center of mass is like squishing the object to a point. By the way, center of mass can be abbreviated as COM. So COM is center of mass. This abbreviation is the bomb.com. Just saying. So instead of writing center of mass 40 million times, you could write COM. So if you have a box, this is my box, where's the center of mass? The center of mass is in the center. It is as if we squish the box to one singular point. That is our center of mass. Well, for instance, I have this frisbee here. Frisbee. So the center of mass of this frisbee is in the center of the actual frisbee. Right? So I could squish this whole frisbee down into one point in the center, and gravity would act on it in the same way. What if this was like a hula hoop and not a frisbee? So basically like the outside rim of this frisbee, but like a big hole in the middle, or like a donut. What if this was a donut? Where's the center of mass? The center of mass of the hula hoop is in the center. So here we have an invisible center of mass. So the center of mass doesn't have to be on the physical object. Like for the box, the center of mass is like on the box. But in a hula hoop, even though you have empty space, like inside the hula hoop, the center of mass is in the center of the hula hoop. The center of mass is also the point around in which an object rotates. So if you think about a hula hoop,
it rotates around its center, or around the invisible center of mass.
Well, is the center of mass always like right in the dead center of something? Not necessarily. So I have this hammer. Where's the center of mass of this hammer? Well, most of the mass of the hammer is right here. So like the head of the hammer is way heavier than the handle. So I have more mass over here, so my center of mass is going to be closer to the part of the hammer where there's more mass. So my center of mass is going to be somewhere over here, not here, which looks like the center. Maybe like lengthwise it's the center, but it's not the center of mass. The center of mass, we're thinking about mass. So if there's more mass over here, our center of mass is going to be closer to where there's more mass. So can free body diagrams only be drawn for one object? Well, no, not necessarily. You can draw a free body diagram on a system of objects, but when you're drawing a free body diagram on a system of objects, or many objects, you still treat that system as one object. So if you're drawing a free body diagram for a system of 5 boxes, I don't know, stacked on top of each other, you treat all 5 of those boxes as one big box.
And then you would draw the forces acting on the system. So the forces acting on all 5 boxes together. Not forces between the individual boxes, but forces acting on all the boxes.
So when you're drawing a free body diagram, you're either drawing the forces acting on one object or the forces acting on a system of objects, but you're treating that system as if it were one object. But just be aware that free body diagrams can be drawn for systems, but regardless, a free body diagram is drawn treating the object or system of objects as one thing. Okay, when we're drawing free body diagrams, we're drawing the forces acting on the object. So if we gotta draw the forces acting on the object, we gotta at least show our object. So if my object is, I don't know, like a hanging plant, do they expect you to draw a hanging plant? No. No matter what your object is, you have 2 options for how to draw your object. You can draw a square, or you can draw a point. Whoop. So whatever you're drawing a free body diagram for, you're going to draw that thing as either a square or a dot. Either one will work. So the dot works because remember we said like the center of mass is like squishing the object to a point. So this point is kind of like the center of mass of an object. There are 3 rules to drawing free body diagrams. Okay, my 3 rules. Numero 1. Number 1, the first rule when you're drawing a free body diagram is that you draw this diagram free of everything else.
The object should be free of everything else.
So your free body diagram should only be the object or system of objects that you are drawing the free body diagram for. So if I want to draw a free body diagram of this clock right here, then my object is the clock, and I need to draw it free from everything else. We don't care about the table, we don't care about the paper back there, we only care about the clock. So our free body diagram is just this object, it is the clock, and the clock is free of everything else. We don't care about all the other objects it's touching. Our free body diagram is of the clock. We care about the forces acting on the clock. So our diagram is free of all other objects that are not the clock. Again, if we were drawing a free body diagram of that clock, don't draw the clock sitting on a table.
Or if I'm holding the clock in my hand, don't draw the clock sitting in my hand. You only draw the clock, if that is the object.
And we are drawing that clock as a box. So your free body diagram should just be a box or a dot all by itself. Number 2. So we're going to be drawing the forces acting on an object. We're going to represent those forces with arrows. So the second rule is that the tail of every arrow must touch the object. So you can't have arrows floating around in thin air. Every tail or back end of the arrow must touch the object.
Not the tip of the arrow. You don't want the pointy part of the arrow touching the object. You want the tail.
And the third rule is every arrow must have a label. So if every arrow represents a force, you have to label every single force. You have to label every single arrow. Let's give some examples now so that you can see how we apply these rules when we're actually drawing a free body diagram.